So welcome back. Today we're going to talk about rotational kinetic energy. The units for rotational kinetic energy, as all other forms of energy, are joules. If an object is not massless and it's rotating, then rotational kinetic energy is part of its total mechanical energy and must be considered. Nothing has changed with the law of conservation of energy. The energy before still equals the energy after. We just now have an additional term which will help us understand some interesting physical phenomenon, such as a tire turning. Yay! An object that has both translational and rotational motion has both translational and rotational kinetic energy. The final two elements of motion that we have discussed translationally, but not yet rotationally, are work and power. Torque does work as it moves the wheel through some angle theta. The work done by torque is equal to the torque times the change in angle. Of course, power is the rate at which work is done. As power before was just force times velocity, in rotational terms, it is the torque times the angular velocity. So let's hit up a couple of problems. In this first problem, we have a solid sphere of mass m and radius r. It's released from rest at the top of an incline of height h and rolls to the bottom. What is its speed at the bottom, assuming it rolls without slipping? And I went ahead and found for you the translational inertia I, which equals 2/5 mr squared. So the first thing we're going to realize is that the energy before equals the energy after. The potential energy before plus the kinetic energy before, that's both kinetic energies, equals the potential energy after plus both kinetic energies after. If we go ahead and use our zeros, we've got at the very top a velocity of 0, so that cancels out this velocity and this velocity. At the very bottom, we're at h equals 0, which cancels out this h. If we go ahead and plug in what we know as values, our h naught for h, v1 as just v, ri, we go ahead and plug in this term. And for our angular velocity, we go ahead and translate that into v divided by r, because of course v, the translational velocity, equals the radius times our angular velocity. And then we're going to go ahead and clean up the equation a bit and then solve for v, and we're going to find that v equals the square root of 10/7 gh. So if we look at the last problem with a variety of objects, hint, hint, we will find, if we do the math, that each type of object will have a different ending velocity at the bottom of the ramp. In fact, the fastest object is one that doesn't roll down the ramp but slides frictionlessly. When using conservation of energy, both rotational and translational kinetic energy must be taken into account. All of these objects have the same potential energy at the top, but the time it takes to get them down the incline depends on how much rotational inertia they have. This is a concept point too. The objects are not slowed down due to friction. They are slowed down because the energy is being transformed into rotational kinetic energy and not just translational kinetic energy. So one more problem. If a water pump on a particular engine produces a torque of 5 Newton meters when rotating at 4,500 RPM, how many horsepower does this take away from the engine? So it's a power problem. Power is simply torque times angular velocity. Now we're given our torque as 5 Newton meters. We need to convert what we're given for angular velocity, the 4,500 rotations per minute, into an angular velocity. If we do all this, do the math, what we're going to end up with is 2.36 kilowatts as the power. But that's not quite what the problem was asking. It was asking horsepower. So our 2.36 kilowatts times our conversion factor, we're going to end up with a 3.16 horsepower. So thank you again for watching. Please check As You Learn for the remainder of this assignment.